Okay, hello everybody. So today we are going to begin our discussion in chapter 11, section 3. And in this chapter and section, we will be talking about simplifying rational expressions as well as identifying values excluded from the domain in those rational expressions. Now, that may make a lot of sense to you right now, but as we move forward here with a couple examples, that'll probably make more sense to you once I show you some problems. So let's get started. So what you see here is we have two algebraic expressions. The first algebraic expression that we have is y squared minus 4, and the second one is y squared minus 8y plus 12. Now, if I were to take those two expressions and divide them, they would look like this. What you see here is called a rational expression. If you recall, a rational number is a number that can be written as a fraction. Well, rational expressions are expressions that are written as fractions. So this right here is called a rational expression. Now, as we do with rational numbers, for instance, 4/8, sometimes those rational numbers need to be simplified or reduced. In this case, both the 4 and the 8 would be divisible by 4. And when we would divide both of those by 4, we would end up with a new fraction, 1/2. Now, that new fraction, 1/2, is equivalent to 4/8. It's just being expressed in a different way than the 4/8 was, but they are the same. Well, that example that I just showed you with fractions holds true for these rational expressions. They also can be simplified upon occasion, and you will be asked to simplify those, which I'll show you how to do that in more detail in a second. So a rational expression is an algebraic fraction that has polynomials for the numerator and the denominator. It says, reminder, the polynomial in the denominator cannot be 0. So if you look at this algebraic expression that we have here, this rational expression, I should say, you can see that the bottom is x plus 2. Now, what we have to make sure that we do, and this is where the second objective was, identify values excluded from the domain. The reason why we will have values excluded from the domain is that there are numbers that would create a situation where we would have a 0 on the bottom. And if you remember, in a fraction, you are not allowed to have a 0 on the bottom of a fraction. So looking at x plus 2, we need to determine what number would make that 0. And it's very simple process to do that. You simply take whatever is on the bottom and you set it equal to 0. And we can subtract 2 from both sides. And what you can see is if x were to be negative 2, if we would put negative 2 in right there, we would end up with a situation where the bottom was 0. So for this particular rational function, this whole rational function, after you would write the rational function, you would also need to write that x is not allowed to be negative 2. And just to show you, if you took this negative 2 and put it in there, you would have negative 2 plus 2, which is 0. So it would make this whole bottom 0, which we don't want to do because you are not allowed to divide by 0. So you can see that we discovered, or we really calculated, what value of x we must exclude from the domain. And in this case, the value is negative 2. So for all of these rational expressions, after you simplify them, sometimes you will be asked to determine what value should be excluded. Now, for these first ones, we're not going to do that. But for these later ones, which will start in number 3, we will do that. Okay, so let's try one of these examples. These first ones are going to be pretty straightforward in that we will just be able to cross things off that you see in the numerator and the denominator. So for instance, for this one, we have the numbers 18 and 20. They are both divisible by 2. That's the biggest number that they're both divisible by. So I will turn the 18 into a 9, and the 20 will turn into 10. So those are completely simplified. Now we need to look at our variables and see what we have. Now we have an a to the second on top, and we have an a to the third on the bottom. Now what that means is a times a on the top and a times a times a on the bottom. So we will cross out the 2 of them from the top, and we'll cross 2 of them from the bottom, and you will see we'll still be left with 1a down on the bottom. Now, the way to think about this is how I showed you, canceling variables from the top and the bottom. Now, the math behind what we're doing is we're actually going to subtract the 2 exponents. So in this case, 2 minus 3, which is negative 1. Now, because the exponent is negative 1, it means it goes down to the bottom. And so what we're actually left with is a to the first power on the bottom. Now, looking at the b variables, you can see I have b to the fourth over b to the first. Once again, you can think about these as having 4 b's on the top and only 1 on the bottom. When I cancel 1 from the top and the bottom, you can see that I'm left with 3 on the top. Now, showing that in this fraction, the b's, this one would completely cancel, and this is a b to the first. 4 minus 1, so we're subtracting the exponents. 4 minus 1 would be 3. So this whole one goes away, and this one would turn into 3. Now, the last ones, we can see we have the variable c. Now, once again, you have 3 c's on the top, and you have 5 c's on the bottom. So if I were to illustrate this for you, it would be c times c times c over c times c times c times c times c. So all of the top ones would cancel, and we would still be left with 2 on the bottom. Now, the math behind that, once again, would be that you would subtract, you would do 3 minus 5. So 3 minus 5 is negative 2. Now, because that number is negative, we would put it on the bottom. So this one completely cancels out, and we make this one become a 2. It is a positive 2 since we moved it to the bottom. And then that's it. We have simplified everything. So now we just need to write our simplified form out. So in the numerator, we are left with a 9, and then we are still left with a b to the third. Now in the denominator, we're left with a 10, and the a was gone. No, it wasn't. That was a lie. There should still be one a left down there, a to the first, and there's still a c to the second. And so right here is our final simplified answer. Now we're going to try another one just like this. This one is just like the last one. It's all multiplication across the top and all multiplication across the bottom, which means we can just cross things out or simplify things. We have a 27 and then an 81. Now, if you can figure out what the biggest number is that would go into those, you would actually see that I thought maybe it would be 9, but if you divide both of those by 9, you'll be left with a fraction that still can be reduced. So to actually show you what the biggest number is, I'm going to divide, and the biggest number is actually 27. So if you do 81 divided by 27, you get 3. So that means 27 divided by 27 is 1, so we can cancel that out. And then 81 divided by 27 is 3. So we'll write our 3 there. Next, we will look at our variables. You can see I have r on the top, and there is no r on the bottom. So that r will remain there. It does not get crossed out with the 27 or any of the other variables. Now we can look at our s's. We have 2 s's on the top, and we have 3 s's on the bottom. So that means the 2 from the top will cancel out, and we'll take 2 away from the bottom. So this will just become s to the first. Now the last set of variables, we have a t to the fifth and a t to the first on the bottom. So that means we have 5 on top and only 1 on the bottom. So I'm going to cancel the 1 out from the bottom, and I'm going to reduce the 5 by 1 because we're canceling one of those out. And so we're still left with 4. All right, so we've simplified everything. Now we just need to write our answer out. So on the top of the fraction, we still have an r, and we still have a t to the 4th power. And on the bottom, we have a 3, and we have an s to the 1st power there. And there's our final answer. Now, if you notice in these first 2 examples that I showed you, they both had all multiplication across the numerator and all multiplication across the denominator, which is what allowed us to cancel things out. Unfortunately, rational expressions aren't always like that. And if you look at this particular expression, you can see that we have addition that is separating the terms. Now, because there's addition separating the terms and not multiplication, we cannot just cancel variables out. You can only cancel out when it's multiplication. So what we have to do in this particular problem is take the GCF out of anything that it can come out. But we look at the numerator and the denominator separately. So forget about the denominator for a second. Let's look at the numerator. Is there a GCF between 4, m, and 8? And the answer is yes, there is. It's 4. So what that allows me to do is take a 4 out and leave what the other stuff behind. So this is what we worked in the last chapter and section, in the chapter 8, 5, and 6, where you can take a GCF out. And that's exactly what I did. I took a 4 out. Now, if you look at the bottom now, you can see that I'm left with m plus 2. And in this one, there is no GCF, so there's nothing to take out. So we will just write another, in parentheses, m plus 2, like that. And so now what you see is there are like terms that are grouped together, the m plus 2 and the m plus 2. Those can cancel, and what I'm left with is 4. And there is our final simplified answer. Now we'll try another one of these. If you look at this particular one, this is going to be similar to the last one, although it's a different problem for sure because there's different numbers. But we're going to look at each part separately, the numerator and the denominator. You cannot just cancel the x's out like that because these terms are separated by a minus. So if terms are separated by a plus or a minus, you need to cancel all of them out, not just one of them. So looking at the x and the minus 3, there is not a like term there to pull out, so we will leave it as x minus 3. Now on the bottom, however, this is a factorable quadratic expression, and this particular one will factor. Remember, we need 2 numbers. Now, I'm going to make this a little bit different. I'm going to make this x squared plus 0x minus 9. Now, the reason why I expanded it out is so it will be in a form that we know how to factor. So we need 2 numbers that add to be 0 and multiply to be negative 9. Well, the factors of negative 9 are 1 and 9 or 3 and 3. In order for them to multiply to be negative, one or the other would have to be negative. So in this case, we would either have 1 or 9 or 3 and 3. One of them has to be negative of the pairs, and they have to add to be 0. Well, the only solution then is negative 3 and positive 3. So you can see these are the 2 numbers that this quadratic trinomial would factor into. So remember, we write our term, our variable first. We draw 2 sets of parentheses, and then we put our 2 factors in, minus 3 and then plus 3. So now what you can see is we were able to split up the x squared minus 9 into x minus 3 and x plus 3. Now we're able to cancel things out because they're in groups that are the same. So in this case, the x minus 3 will cancel the x minus 3. Now, when everything cancels in the numerator, we still need to put a 1 there as a placeholder. And on the bottom, we are left with x plus 3. There is our final answer. Okay, so the last thing that I want to show you is what you do as far as the second thing that I listed here, which is identify the values excluded from the domain. In order to identify the values excluded from the domain, you need to look at the denominators of each of the original expressions and determine what value you cannot plug in there. So if we look at number 3 here, you can see we have m plus 2. M plus 2 is not allowed to be 0. So if I write m plus 2, I will say it cannot be 0. And to solve that, I subtract 2 from both sides, and I get m equals negative 2. I should say m cannot be negative 2. So this would be our restriction for this particular rational expression. Now in the next one, you can see I have x squared minus 9, and that one we will set not equal to 0 and solve that one. Now in this particular one, we would need to add 9 first, and we would get x squared equals 9. Now, in order to solve this, in order to get rid of a square, you must square root. That's how we get rid of a square. Now, when you take a square root, you will get x equals, and the square root of 9 is 3 or negative 3. So there are our two answers for this one. So in this second one, we would not be allowed to plug in 3 or negative 3 in for the x that's in the bottom of the original expression. So that's what I have for you today, guys. I hope that made sense. And as always, if you have any questions, feel free to email me. Have a great day.